Okay.
So, to begin, Dr. Ashtekar, what would you say is loop quantum gravity and how does it differ from loop quantum cosmology?
Okay. Right. So, in broad terms, loop quantum cosmology is a subfield in the sense that it is a application of loop quantum gravity to the cosmological setting. So, your first question about loop quantum gravity. So, basically, it's a approach to unifying general relativity and quantum physics. And there have been many approaches, and in some ways, I mean, uh, people are puzzled. But the point is that basically, uh, different communities have come to been attracted towards this problem over last several decades. So some communities came from particle physics, some communities came from general relativity, and the ones from particle physics, sort of they, through a series of ideas, they went into evolved into string theory. And
Hmm.
those who came from general relativity side also evolving through many stages arrived at loop quantum gravity. And the reason I give this background is that it's the fundamental um, views about how to approach a problem is deeply influenced from where you come from. So, because you sort of your past successes of your field always tell you what or suggest to you what you should focus on, what you regard as primary, and what in
Hmm.
some sense will take care of itself after the first things are solved, the basic fundamental things are solved. So in loop quantum gravity, one takes the Einstein's general relativity, the central message, very seriously, and that message is that gravity is encoded in the very geometry of space-time.
Hmm.
And therefore, even for Einstein to build general relativity, he had to use a new syntax. I mean, until general relativity, people were used to doing physics, partial differential equations, in space-time coordinates, etc. And Einstein came to realize over the years from 1908 to 1915 that what one had to do was to use the uh, area of mathematics called Riemannian geometry. It's a subfield of differential geometry which sort of deals with metrics and so on, which determine the distance and the causal structure in space-time. Uh, so, I mean, this philosophically, the basic idea is that in space-time, in general relativity, there is no background space-time. In
Hmm.
Newtonian physics, there is space and time are given to us. They are like a stage on which things happen.
Hmm.
And, everything like stars and sun and you and me, and we are all actors which act on this fixed background. In general relativity, this stage disappears. There is just no stage. Everything is an actor, including space and time itself. So that may be a kind of philosophical big difference is that
Yeah.
everything is dynamical, everything is actor. There are no spectators. There is no stage on which things happen. Everything is just interacting with itself. Stage, if you like, joins a troupe of actors in here. And therefore, since space and time is also an actor, if you like, in here, it changed, it is a dynamical entity, it is a physical entity, just like tables and chairs around you.
Hmm.
And so it can be acted upon and it reacts back. I mean, that's what Einstein taught us that, uh, sort of matter curves space-time, that it can be acted upon. And in return, the curved space-time tells how the matter, how to move. So there is I mean, yeah. So it's a physical entity. Now, if I look at physical entities, so it is very much like matter, like normally we think of matter as one physical entity, and electromagnetic waves or the electrons or the things around us, Earth, which is made of matter, as being a physical entity. And now what we know is that for matter, quantum physics has taught us that we have to understand it in terms of its atomic structure.
Hmm.
And so the idea here is that if space-time geometry is also a physical entity like matter, then it should also have some atomic structure. And that atomic structure is something that you should explore using quantum physics. So that is the idea of the quantum.
That's very interesting. I never heard this idea that particle physicists are more geared towards string theory and students of relativity are more geared toward loop quantum gravity. I guess it kind of makes sense now that I think about it, with that background. But how did you first become interested in researching quantum gravity and eventually loop quantum gravity?
Well, quantum gravity was something that I was interested in from very early on as a graduate student already. In fact, one of the first papers I wrote was a review paper with my advisor on what was known in quantum gravity and such things. So that was a long time ago. It is still used by people, is surprisingly, but it was 50 years ago. So I mean, it's basically because that is the outstanding fundamental, conceptually fundamental problem in physics. I mean, there are many open issues, right? We don't understand many, many things. We don't understand what is dark matter, if there is dark matter, and if there is quote unquote dark energy, or is there a cosmological constant or some other field? We don't, but these are specific questions about what constitutes the universe. It's about the constituents of the universe. It is not about underlying laws. And
Hmm.
well, I was always interested in the fundamental laws. I mean, just like, general relativity is a fundamental, or Newtonian gravity was a fundamental law, which explained how solar system, we can operates, and we can explain everything, right? I mean, the solar system. But that was too limited. And then Einstein has general relativity. There's also much grander law. It's much more unified. I mean, to sort of give you the sense of why these laws and so on are so important is because of universality. For
Hmm.
example, what Newton taught us, which is I believe most people don't realize, is that there's a fundamental law of motion, of gravity, with how things are attractive, and then there are laws of motion. And in fact, the laws that govern Earth going around the sun is exactly the same law that governs the apple falling on the Earth. So you would say, oh, wait a minute, but if that is the case, why doesn't Earth just fall into the sun? And the own equations are exactly the same. They're shocking. But the initial conditions are different. Earth started not pointing towards the sun, or it was not at rest. If Earth was at rest, then it would actually fall into the sun. But
Hmm.
it was not at rest. It was actually moving in a tangential direction. Whereas the apple is just sitting there. So only the initial conditions are different. Laws are the same. And this is something that is very, very important. This is very universal about it. And the same thing is true with general relativity. Einstein elevated it not to the solar system, not to just Apple and the Earth or the planets, but to the whole universe. That there is a single equations. They apply to everything. They apply to Earth, they apply to Apple, they apply to the whole universe, how the universe evolves, etc. So that universality and that always, I mean, it's like a philosophical interest, basically, that it is understanding some very deep principles which govern everything we see. So that is what attracted me to quantum gravity to begin with. And then loop quantum gravity is because I founded loop quantum gravity. So I started out, it's difficult to say, wow, what attracted
Yeah, yeah,
me
yeah.
because I founded it. But I founded it I mean, I had a lot of motivations, which were a lot of inspiration that came from some ideas of Roger Penrose's, some ideas of Ted Newman, and so on and so forth. But loop
Hmm.
quantum gravity is inspired by that, but is a different approach. It's not twisted theory of Roger Penrose, but it is really quite different. And it has made much more concrete progress than in terms of physics, not mathematics, but in terms of physics, than say something like twisted theory. So it's really, it is there was a bunch of works that had been done over many years, right? Since the 1960s, uh,
Hmm.
on idea that, well, space and time are geometry, and then how do you quantize geometry, and etc. But those things were very, very still mathematically very formal,
Hmm.
and I was not happy with that. And so I tried to make something which was much more mathematically precise. by borrowing ideas from different areas, but then consolidating them in a whole thing. And one of the some of the ideas were basically came from what is called as gauge theories, like
Yeah.
electromagnetism or quantum chromodynamics, which governs the quarks and the gluons and the nuclei. And so and then, as I said, from twistor theory. But these ideas were sort of, brought together in a coherent way. It was not just slapped together, but
Hmm.
as a whole in
Yeah.
loop quantum gravity.
And you mentioned Penrose, he's very famous, of course, for the conformal cyclic models. But the bounce model that we have is not exactly a cyclic model. Can you explain what the difference between those might be?
Yeah, there's a big difference. I mean, in I mean, Penrose doesn't have anything quantum. There's no H bar in it. Penrose's equation. It's all classical equations that are modified in certain sense.
Mhm.
Whereas almost everybody else, not just loop quantum gravity, almost everybody else believes that when the space-time curvature becomes very large, like the Big Bang and so on,
Mhm.
then quantum physics becomes important. Whereas in Penrose's ideas, quantum physics is never important. What happens in the cyclic model doesn't have is not because of quantum effect at all. And so that it's a dramatically different uh, ideas, if you like. Uh,
Mhm.
it is very difficult with classical ideas to explain the cosmic microwave background structure in any detail.
Yeah.
Every explanation of cosmic microwave background structure is rooted in quantum mechanics. And so if you don't have quantum mechanics, then it's very difficult to explain that. So, that I think is a fundamental difference between what Roger does. And Roger was my postdoctoral advisor. I
Mhm.
just gave
Yeah.
us a Zoom seminar last week in Oxford. And so we talked about it and so on. So, we communicate all the time. And
Mhm.
so the two ideas are, I mean, it's very different. I mean, it's we are bringing in almost everybody, including loop quantum gravity, brings in quantum mechanics as an essential way. It is because of there is a h bar, Planck's constant, that there is a bounce. If h bar goes to zero, bounce disappears and you get back classical general relativity with this Big Bang singularity. So, yeah. So for us, the bounce occurs because of quantum effects, whereas for Roger, it does not. And the point is that even if I look at big objects like neutron stars in the sky, they exist only because of quantum physics. If
Yeah.
quantum physics wasn't there, neutron star would collapse and form a black hole in no time at all. I mean, but it is because of certain quantum repulsive forces that are uh, purely quantum mechanical in origin. They balance gravitational attraction, and that's why we got things like neutron star. And so, what happens to us? I mean, this is not a you know uh, by any means complete or even a good analogy, but there's a
Mhm.
qualitative similarity. What happens for us is also that the quantum effects of geometry, not of matter, but of geometry, create an effective repulsive force only at when the space-time curvature is extremely large. Until then, these effects are it's there, but it's absolutely completely negligible. I mean, you could never
Mhm.
measure it with any
Yeah.
apparatus that you can think in many centuries, if you like. But when the matter collapses, either inside the black holes or the Big Bang, when the densities are I mean, the Planck density is 10 to the 90 grams per cubic centimeter. Nuclear density is 10 to the 14 grams. So there is 18 or 80 orders of magnitude larger. So this we don't have any laboratory experience with such object. We really have to go to understand quantum gravity effects. We really have to go near the Big Bang or inside the black holes and such regions. So there, this quantum nature of geometry. So
Mhm.
that's the point. We're going beyond Einstein by using a quantum geometry. So we're providing a new syntax for all of physics. So this is philosophically interesting that what Einstein did was to provide a new syntax to do all of physics. And that syntax was this Riemannian geometry. What we've done is to create a new syntax for all of physics. And that syntax is called quantum Riemannian geometry. And so it differs from Einstein's Riemannian geometry that Einstein used when the curvature becomes very, very large, where matter densities become very, very large. They become, so to say, Planck scale. Then these new effects come into picture.
And we spoke a little bit about the bounce there. Why does loop quantum gravity predict a bounce? And can you just reflect a little bit about, you talked about the quantum effects, but what does that really mean when we look at the theories?
There are corrections to Einstein's equations, and they're not put by hand. The sign and so on is not by put by hand. They're systematically derived from first principles in loop quantum cosmology,
Mhm.
which is an application of loop quantum gravity to
Yeah.
cosmology. And then when these applications are done by step by step, then one finds that there is an extra term which can be interpreted as being a repulsive force. So in absence of that extra term, and that is really, it's only when the matter density becomes compared to the Planck density, which is, as I said, 10 to the 90 grams per cubic centimeter. And nuclear
Mhm.
density is about 10 to the 15. It's actually 19, 10 to the 93 grams per cubic centimeter, and nuclear density is only 10 to the 14. So that there's a huge order of magnitude. You don't remember. I
Yeah.
mean, sometimes it's good for you to write down these numbers 10 to the 80 and how big is it 10 to the 80. So, for example, if you take two dollar bills and stack them on top to on one another, and if you have 10 to the 80 of them, where do you think you will go with 10 to the 80?
10 to the 80, maybe to the sun.
Not quite to the, but it's definitely beyond the moon. Yeah, you'll go beyond the moon there. So it's 10 to the 80 is a huge, huge number, right? I mean, 10 to the 80 would be, yeah, yeah,
Wow.
yeah. So it's a huge number. Yeah, beyond moon. I mean, way beyond moon, so, but not quite to the sun yet. Yeah. So it's huge. I mean, so it's a big number, and so uh, when the matter density becomes that, then this force is important. So it is suppressed by this Planck density. So if it's really, there's a correction to quantum to Einstein's equation, but the correction term is the matter density rho, it is usually written as rho as a Greek letter, divided by rho Planck, and rho Planck is 10 to the 19. So until the regular matter density becomes of the order of 10 to the 85, 10 to the 87, 10 to the this effect is totally negligible. But then it becomes, it really overwhelms everything else then and causes the bounce. So the first time when we realized this, I didn't believe it actually when we did these equations with two of my postdocs at that time. Now they're senior professors, both of them, but they were postdocs in 2006. And so I wanted to do, this was first done using numerical simulations by, putting the things, the equation on the computer and solving them on computer. So we changed the initial conditions, we changed all kinds of things, right, to see if it is really robust or we just got some spook, some very, very special conditions being advertently put, and that gave us this. Is something that is happening generically? So in fact, we did not. I mean, I published this for years. I mean, that for months, not years, for months, several months. I, I, you know, kept doing all kinds of checks. And then finally, when enough checks were done, and I also understood without putting it on computer analytically, mathematically, as to why this qualitative differences are occurring. And that is when we published the paper. So there are some popular articles, I can send you the links if I remember, so I can write
Yeah.
down links to you. There's also a YouTube video that you might want to look at if you're interested in the Big Bang.
Hmm. Yeah.
It's only 10 minutes long, or 15 maybe. But it has Roger Penrose, Stephen Hawking, um, then Willinkin, and I mean, they're leading cosmologists. I was also asked to speak there. But the important thing was that we did not know that other people were speaking. We were interviewed completely separately. But
Hmm.
then at the end of the day, we say very similar things.
Hmm.
And so, I mean, it's not that we all agree on everything, but qualitatively, we all agree that there was no Big Bang, that the Big Bang is not, is just an idealization of general relativity. That I think is a very striking thing that people coming from completely different areas are saying this. But I think the first people to do this mathematically were people in loop quantum gravity. Yeah, I mean, correctly mathematically.
When you say no Big Bang, you mean like the singularity Big Bang. There
Right,
was still like a
exactly.
hot expansion of
That's
space,
very
right?
good. Very, very
Okay.
good. Exactly. So very good. So I think now when the general belief among all leading cosmologists is that Big Bang refers to a hot phase,
Yeah.
exactly what you said, in the early universe, not a singularity or not the origin of the universe either. Right? I mean,
And
that's the,
what does that say about black hole singularities? Do we kind of have a similar idea that it's
yeah.
just a
So there's a lot
failure
of
of our
work in
math?
loop quantum gravity on that, and the black
Yeah.
hole singularities are also resolved. And the black hole singularities are more complicated than the one in cosmology. It's just
Mm.
that in cosmology there's much more symmetry than for black holes, and so you um, mathematically simpler. And so, but we are shown that is the case, right?
So based on the current models that we have, do we have any idea of what a pre-bounce universe may have looked like?
Yeah, yeah. So I mean, each of these things tell us what the pre-bounce universe looks like. I mean, it's not completely symmetric. It all depends on the initial conditions that you give, and it's sensitive to the initial conditions. So we don't know the initial conditions with sufficient accuracy, so you cannot be completely. What we're doing is the following: we're taking the initial conditions today and evolving it back in time. If you evolve back in time using Einstein's equations, you get Big Bang and physics just stops. I mean, everything.
Mm.
John Wheeler used to say, "Smoke comes out of computer."
Yeah, yeah, yeah.
So, physics just stops because things are infinite, and so we can't calculate anymore. So the equations of loop quantum cosmology don't break down. You can go back, and so you can see. But what precisely would happen does depend on you know very specific initial. I mean, the knowledge of the conditions today very, very accurately, and we don't have that much accuracy. So qualitatively, we can see what happens. That there is, we can say that if there is a positive cosmological constant, what will happen? If negative cosmological constant, what will happen? If there is zero cosmological constant, what will happen, and so on. If the universe were closed, that is to say, if the density in the universe was bigger than the certain critical density, then the universe will recollapse. We don't believe this is the case from known data. But philosophically, the statement is that in general relativity, depending on the initial data, the universe behaved very differently. If it is if if it is spatially flat, then it just expands out forever. But if it is spatially like a closed, like that of a three-sphere or higher genus, higher topological objects, then
Mhm.
it sort of expands out. It starts the Big Bang, it expands out, and then recollapses again. Whereas if it's flat, then it's Big Bang, and then it just goes off. So
Mm.
similarly, in loop quantum cosmology, the statement is that the Big Bang is resolved, so you go back in time. And then the statement is that there is just one universe which just goes back in time. But if it is a universe were closed, then you can go back in time or you can go future in time. Einstein would say that you've got singularities at both ends, whereas
Mm.
here in loop quantum gravity they are resolved. So then there are many, many cyclic things, and these are worked out in great detail between 2005 and 2010. Um, People work them out in great detail.
Is there a misconception you often see people maybe in the public make about these theories?
There are many mixed. Most of it is misconception. I think there's very few clean things. Yeah.
And what would be an example of that?
Um, I mean, they think of, for example, misconception even for general relativity. They think of the Big Bang like a firecracker or something, or they
Mm.
think that the universe was started with a point and expanded. That's not true. If it's spatially flat, then the universe is actually always infinite. Even at the Big Bang, it is infinite. It doesn't,
Mhm.
and so it's still expanding. But
Yeah.
infinite things can expand,
Right, the
can
Big Bang
contract,
happens
remain infinite.
everywhere. It's
It
happening.
happens everywhere,
Yeah.
exactly. It's not that it starts with a single point and then goes off. Or, um, I mean, people also have some prejudices. Or they just say, "Oh, I don't think that can happen." I mean,
How did we kind of get this? Sometimes in popular physics, you'll hear this notion, especially in the past decade, that there's no before the Big Bang. It's like saying north of the North Pole.
Yeah,
That's
that,
how did
that
we
I
kind
think
of
is
get that idea?
that is true in general relativity. I mean,
Hmm.
general relativity is really true that there is nothing before Big Bang because space-time just stops. Space-time is an edge. It's a boundary, and things are infinite there, so you cannot continue. I mean, if you anything which tries to go will be completely crashed and also and absorbed into the singularity. So, in general relativity, is not just matter which stops, but space-time itself ends at
Yeah.
that period. So that is the idea from general relativity, and the statement is that no, space-time doesn't end. I mean, if you take into account quantum physics, it doesn't end. You can go back and forth.
You were mentioning that you had already had these models of loop quantum gravity, and then your postdocs came along and they showed you that some of these models in loop quantum cosmology can lead to a big bounce.
No,
Can
no,
you?
I did not have any models. So, look,
Hmm.
this is the first investigations we're doing with postdocs showed that
Yeah.
there was a big bounce. It's not that there was a model before. I mean,
Mm.
this was the first time that I was doing things in detail. And
Yeah, yeah, yeah.
yeah, good.
Okay.
Martin
Mm.
Boyle was also one of the postdocs, but that was earlier on.
Okay, I understand. So, is it possible to construct a bouncing model without this? And is it possible also vice versa to
Without
have a
this meaning what?
model of loop quantum gravity that does not have a bounce?
Uh, First of all, what do you mean without this? Can you? First question was, can we construct? A,
Yeah,
yeah.
I mean, can you have like a bouncing universe without loop quantum
Yes.
gravity?
Yes. There are other models which also give you bouncing. Bounce is not uh, um, a unique sign of low quantum gravity. It's a sign of many theories in which, but if you, therefore, it's not, we cannot distinguish just by looking at bounce. We will have to look at much more detailed things like, you know, um, the early universe, cosmic microwave background, what are the parameters of the early universe. So
Hmm.
one of the things that so, uh, my younger colleagues and I showed 3 years ago, 22, that there's a standard model of cosmology which has 6 parameters, and
Hmm.
then 5 of them have been accurately measured. By accurately, I mean with less than 1% error, so to say.
Yeah.
But the sixth one, which is called optical depth tau, that is it's still not charging. So anyway, we have to quit soon, so it doesn't matter. It's all right. Yeah. So sorry, so you're asking me something, and I just realized the computer is losing the battery. Oh,
Yeah, I was asking you about bouncing universes outside of loop
yeah,
quantum
outside.
cosmology.
Right, right. So there are other ideas which also can lead to bounces, but the main thing is that you have to look at the detailed predictions to see if, in fact, the detailed connect predictions are going to be val. I mean, they differ in bounce is a more qualitative thing, but then what effect does the bounce have on this cosmological parameter? So we've got the 6 parameter cosmological model, out of which 5 parameters are very well measured, but the sixth one is not. And I mean, we have the thing is that to make connections with observations, you have to do some simplifications because you cannot. If you try to do it exactly, the problem is way too complicated. There's no way
Mm.
to sort of make headway. And so, I mean, this is true not in just cosmology. Every area of physics, this is true. In QCD, quantum chromodynamics, also. I mean,
Yeah.
one makes approximations, and then one sees if they're true or not. So, I mean, that but with experimentally true or not. So we have done that, and what we find is that um, that uh, that the one of these the last parameter, optical depth, is about 10% higher in in our model or in our calculation under our assumptions than the optical depth, than the standard cosmological parameter, so to say. And this is the least well measured parameter. For all
Hmm.
of the parameters, for the other 5 parameters, there's only less than 1% error, but for this one, there's 13% error. So
Yeah.
therefore, we cannot really tell. I mean, both of them are allowed in the because of these big error bars, right, at the
Yeah.
moment. But because it is so poorly measured, there are several missions which will actually measure it more accurately. And at one stage, they claim that they should be able to measure it within 1%. If that happens, that will be great. Right now, they have brought from 13% to about 8%. And as they have done it, the value is shifting towards loop quantum gravity, loop quantum cosmology to our value. Now, but I'm not, I'm happy that this is happening, but this is not conclusive at all because the error bars are still 8%, not 13, but still
Yeah.
8. And 8 is still large. And so, it could happen that it goes away again or something. So we'll have to see. I mean, in other words, loop quantum gravity is fine in this currently, but if it is brought to 1%, maybe we are way too high or something. Well, we'll have to check. But to me, what is important is that one can distinguish between various of these models, bouncing models that you talk about, by such experimental predictions. And so that is uh, the thing that. Okay. I think we should wrap up. So
Yeah, and a question about that. These other bounce models, do they also get the bounce from the same constant in relativity that you mentioned?
no, I think like Penrose gets it without any quantum
Yeah.
mechanics at all. So it's not. It's completely different. And then they cannot really do these calculations of the kind that I was telling you about the cosmic microwave background and detail how much what the parameters are and such thing. They cannot do that.
Yeah.
Other models, there are other models which actually do use quantum mechanics, do use perturbation theory, and so I think one should. Uh, uh, yeah, so I think one has to take them and see the predictions and check with the experiments and so on and so forth. I think it's good to have rich ideas, and
Yeah.
but ultimately, the observations is what is going to decide. And our job is really to sort of try to explain the observed universe. If it turns out that we're barked the wrong tree, because or most likely what will happen is if it is not right, then that means that one of these additional assumptions we made in order to arrive at results is not is not correct. So we'll go and revisit. I mean, this is what happens in QCD every
Yeah.
day. So that's why I'm saying it's not something that is just wishful thinking or something, but it's more constructive way of what we should be prepared to do should it happen that somehow the observations say that no, your value is too high. Then why did we get this value too high? So what are the assumptions we made? We look at them carefully one by one, and if it doesn't work out, then we just drop it.
Um, Recent research from DESI has suggested that dark energy may be decreasing. How does the discovery that dark energy may not be constant and may be decreasing affect how we look at these models? Is that better for us, right? Or is it kind of,
No, no, it doesn't really affect this early universe very much at all. It affects late universe, what happens
yeah,
in the distant future. The early universe models are not, I mean, what happened very early on doesn't change very much at all with these models. I mean, so it really has to do with what is going to happen late. I mean, the thing is that if you're too off, right? Then you will not get nucleosynthesis. You will not
mm,
get all kinds of things, right? I mean, reionization. You would not get. So Daisy cannot be very different from. In other words, uh, it's not a cosmological constant. It may be something else, but it cannot be very different. What? Okay, let me explain better. So they're looking at backtrack. Okay. So in this standard cosmological model, right? I mean, we got many components. So one component to the energy equation. I mean, there are Einstein's equations, which with the symmetry give us what is called Friedmann equations, which are just
yeah.
Einstein's equation but with a lot of symmetry. Okay. And that in this Friedmann equations, you have got um, um, energy density on the right hand side. And so this energy density can come from electromagnetic waves. So it is, uh, the cosmic microwave background and various things. And there'll be energy density coming from matter, which is like us. They can be also dark matter. There can be regular matter. But this is also what people like to call dark energy. But dark energy just means that there's a cosmological constant there.
Mhm.
And what we know is that nobody does that. That in the early universe, this contribution of dark energy was completely, totally negligible. As we, but the point is that dark energy, okay, matter is expanding out.
Mhm.
Because matter is expanding out, its energy density is obviously decreasing because you've got the same amount of matter in a larger volume later on, later in time. So the density is decreasing. And so we know that the density is going to decrease like some power of t as time is going on. The same thing with the energy decreases with some power of t as of, for the electromagnetic, for the radiation, the universe. But what happens is that the energy, so to say, in the cosmological constant, this contribution for the cosmological constant to this right-hand side of Friedman equation, it remains constant in time.
Mhm.
So even if it was minuscule in the beginning, right, it was completely negligible in the beginning. So you can even put it equal to zero. In fact, that's what one does in the early universe because it is so small that calculations will not see it anywhere. But all of the densities are diluting as time goes on. There's some power of time. So of course, there will come a time in which the energy density in light or radiation and energy density in matter has decreased below that in the cosmological
Mhm.
constant. And then the cosmological constant will start dominating. And we are close to that, or we're just around that time that transition appears. So that is why what replaces cosmological constant is going to be important at late times. It's not going
Mhm.
to be important at early times.
Right. I guess I was kind of thinking that the acceleration constant is decreasing, so you have like a decreasing and it kind of lets you have that bounce. But I guess that's not really the right way to think about it because
Right.
you
As you
I
go
was
back.
talking with Dr. Boswell and he used the example of a sponge for these for loop quantum gravity. Do you think that's a good kind of analogy to use?
The sponge is an analogy that is not a loop quantum gravity analogy. That is due to John Wheeler actually. He
Hmm.
called it space-time foam, and he sort of, the idea was that there are going to be topological fluctuations near the Planck scale, and
Hmm.
that those topological fluctuations, he was thinking of them, looking at them as a sponge, in which that small scale. So space-time really resembles like a sponge was his point of view. But that idea was never made mathematically precise. I don't mean prove theorems, but what exactly do you mean by sponge? What is the mathematical object that we're talking about? So that was never done. But
Yeah.
in loop quantum gravity, what we have is more what it's called, the spin networks or graphs. So the picture is really the microscopic picture is not that John Wheeler gave. I mean, it all depends on how rough you want to be. If you want to be rough to just say, oh, you don't have continuum, you got something else, and then sponge is something else, then that's fine. Okay. So a
Yeah.
sponge is just going to represent that instead of having continuum, no structure at microscope, there's some structure, then it's okay. But if you want to take it anything beyond that, then
Hmm.
the idea of a sponge is not okay. You
Hmm.
really have this um, intricate spin networks, that the one dimension excitations of geometry are one dimensional. I mean, which is
Hmm.
a bit surprising that they're one dimensional. It's like threads. I have this shirt here, and if I look at this shirt, then you see that for all practical purposes, it is two-dimensional. Or your shirt, you see how you put your hand on it, says, of course, it's two-dimensional. But you just
Hmm.
take a microscope, uh, magnifying glass, and look at your shirt, and you'll see it is one-dimensional threads, right? It's
Yeah.
one by, but the threads are so tight that for all practical purposes, you got this picture. And so the same thing is true with space-time topology and loop quantum gravity. For all practical purposes, it looks like a continuum under normal circumstances, except when the curvature is very large and this fabric, so to say, tears. But
Hmm.
until then, it is really these threads. So the more faithful, accurate description is that space is woven by one-dimensional threads. Spatial geometry is woven by one-dimensional threads. So there are things called spin forms and which say how space-time is supposed to look like. Space itself is really one-dimensional threads. There are graphs which are sort of going around everywhere, but they're very, very thick, like just like the shirt. So therefore, you got an illusion of continuum.
Hmm.
But so that I think is what loop quantum gravity says. Sponge analogy came from John Wheeler
Really. Yeah.
a long time ago. I mean, like in '68 or yeah.
Can you tell me why the CMB might be important to these models and what we may be able to learn from it?
I think CMB is the only signature we get from the early universe. Now, one might say, okay, but what about black holes and such thing? Well, if you look at astrophysical black hole, like even a solar mass black hole, I mean, the bigger the black hole, smaller is the curvature on the horizon. For
Yeah.
example, the supermassive black holes that are the centers of our galaxy, curvature near the horizon of these black holes is less than that on Earth. It's very so it's for solar mass black holes, of course, is much larger than the curvature on Earth. But even then, it is very negligible compared to the curvature in the early universe. So if you are at the horizon, if you are near the singularity of the black hole, but then that is inside the horizon, then the curvature is much higher. Then it will be comparable to what is happening to the Big Bang or something. But on the horizon, the curvature is very low. And therefore, the observations that we're getting from LIGO, anything, I'm very skeptical that we're going to see any definitive signature of quantum gravity there. So the only place where such curvatures are very large is the early universe. And we're getting information from there through CMB. So CMB is a place, they are the messengers that are coming to us from an era where the curvature was very large. By very large, I mean, it's still about 10 to the minus 12 times the Planck scale. So it is still small compared to the Planck scale, but it's 10 to the minus 12, whereas on a horizon of a solar mass black hole is going to be 10 to the minus 72. So it is not a. I should look up these numbers. It could be 76 or something, but it doesn't matter. It is so completely minuscule compared to the Planck scale. Whereas here, it's 12 orders. So 12 orders, maybe one can see some signatures, and that's the reason why the early universe is very important.
And do you believe that we can really know what the pre-Big Bang universe may have looked like without fully developing a theory of quantum gravity?
Yeah, I mean, usually, I mean, like for the atomic physics, you didn't need full quantum field theory to know understand what is atomic physics. Ordinary quantum
Mhm.
mechanics was enough. You applied quantum mechanics to simplified situations, making assumptions about symmetries and such thing. So that's what we're doing about in cosmology. So I think, I mean, I don't mean you'll get most accurate picture, but you'll get a picture which is darn good. I mean, about what is happening just using the symmetric models in loop quantum cosmology.
Yeah.
But one has to look at various possibilities. One cannot just look at one model and say, "Oh, I found it all." I mean, what to look at us, what the assumptions are. But if you look at some total of models of loop quantum cosmology, then I think they are giving you a fairly very good picture of what is happening before. Doesn't mean that it's accurate picture,
Mhm.
but it will be very surprising if it's qualitatively completely different.
What major problems in cosmology, like what is the big problem in cosmology that a loop quantum gravity or a loop quantum cosmology model of the universe solves?
Um, I think I don't want to say this is a big problem but it's a problem. I mean, namely that the CMB, cosmic microwave background, has anomalies.
Mhm.
Most of it fits it with the standard model. We've got some standard model, as I was saying, the 6 parameter model, and that explains this cosmic microwave background fairly well. But there are anomalies. What does anomaly mean? That means the theory is predicting something and observations are not agreeing with it to some accuracy. Now, if you have got one such anomaly, that says that, well, it means that we live in a universe which is, if you just did a statistical churn out universes by statistically with probabilistic thing that we know about it, then the universe will live in with this anomaly will be 1 in 1,000, and people don't. They say that's fine. There's no problem. But if there are two anomalies, then the universe we live in is 1 in 1,000,000. Three anomalies, then it's 1 in 1,000,000,000. So
Mhm.
then, the odds stack up against you, and there are more than three anomalies. So it does look like the universe we live in is rather special. And so it's very, very special, so to say. Uh, but then that suggests that maybe our theoretical model is not so good. Maybe there is another theoretical model in which the universe we live in is, within the standard deviation of probabilities that the model predicts, so to say, and not tail of the Gaussian, so to say.
Yeah.
And so you may have better model. So what I'm saying is that any one anomaly in the cosmic microwave background is not alarming, but there's a bunch of them together, and taken
Hmm.
together, it is alarming, and we should be addressing them. And something like loop quantum cosmology, that's what we're trying to do. This, it addresses anomalies, and that is why we're saying that the parameters of the universe, the six parameters, are not what standard model says. That's slightly different. And if that's slightly different, then in fact we can account for these anomalies. In other words, they are no longer anomalies. Uh,
Yeah, yeah,
they are under the uh, one of the standard predictions. They're not something which are they're not super exceptional. They are within the range of, if you've got a Gaussian, then something within one sigma, in the one standard deviation is allowed. I mean, it doesn't, your universe will not be at exactly the peak of the Gaussian. It will be slightly away from the peak of the Gaussian, but it should not be at the tail of the Gaussian. I mean, somehow then
yeah.
that would say that's very, very unusual. I mean, if you take wealth distribution in the United States, and then the statement is that you ask a random person in the street. I mean, that person is not going to be at the peak of the Gaussian at all. But
Yeah.
there'll be some width, and everybody will fall in that width, except for Gates or some. They will be at the Gaussian and tails here, right? I mean, and the idea is that, well, if you have a theory, it predicts such a probability distribution, then what we see should be in the middle and not, so to say, at the end.
Mm,
The statement is that if you have got more than two or three anomalies, then that means that your model is predicting that the universe we will see, according to your model, is at the tail of the probability distribution of your model.
mm,
So therefore, maybe there is some better model in which the universe we see is more or less in the middle, and that's what we're trying to do with loop quantum gravity. And we have handled of some anomalies together, and that's the progress that has been made.
well, thank you so much, Dr. Ashtekar. I really enjoyed this conversation. Thank you
Okay,
so
so
much.